the last lecture, I gave two examples for finding the series solutions. One is that is for, of course, second order equations, but even for the first order equations, suppose we have, so these are the kind of equations where say y at 0 equals to 1. Okay, so these are the solutions. You can find the power series solutions. That is you can write the Taylor series solution. Okay, so this has the Taylor series solution. That is because I can write the Taylor series of this function from the given data. And also because the e power y is a real analytic function. Okay, so because of that you can do this. Now if we take the equation like y prime equals to mod y, okay, with y at 0 is 1, y at 0 is not 1, it is say 0, mod y plus 1, let me take mod y plus 1. So now here you cannot say whether I can write a Taylor series. Okay. Whether you take mod y or mod y plus 1, we can't write the Taylor series because this function is not real analytic, is not differentiable. So you will be stuck even for finding y double prime at 0. So this itself is a problem. I can't find y double prime at 0. Therefore, Taylor's series you cannot apply. Therefore, Taylor series is not useful. Taylor series method or the series method you cannot apply in this case. Okay, you cannot have a series that converges to a solution of this equation. So then what to do? That is, if you see the equation, it simply says that the derivative is given to us, the slope of the equation is given to us, slope of the curve is given to us, and we have to find the curve that is passing through this y at 0 is 0. Right. So for it's basically inverting this equation. You just need the function which is just a differentiable function. So once if I write a Taylor series, means that the function is going to be infinitely differentiable. So what I'm looking at is by the Taylor series solution is I'm looking at a function which is an infinitely differentiable function satisfying an equation which involves only the function and its one derivative. So that may be the case that we have to look at. That is, can we look at just the functions which are differentiable? Okay, so if you see if this is the C infinity class of C infinity functions, so these are all like this, right? C1, C2, they're all like this, all the Cn's, and there is a big class of functions here, which is the set of continuous functions, and below that is the set of C1 functions. Okay, so this is C1 functions, that is differentiable functions. So we just need to look at, we need not look at only in this class, we just look at the entire class here. Okay, we look at the entire class here. So there could be some functions which are just differentiable and satisfying this equation. So how do we obtain such kind of solutions? Of course, if there is a method, that method will give us a solution. But in the absence of methods, whether we can find or we can show that there is a solution and then try to approximate it by some approximations. Okay, so we are going to look at basically the equations which are called the semilinear. Semilinear these are the equations basically of the type x prime t is equals to f of t comma xt. So these are the type of equations which are called semilinear. That means the highest order derivative term is a linear term. Highest order derivative term in the equation is a linear term. Okay, and this f is any function, a function of two variables. F is a function of two variables. Okay, that is t comma x going to ftx, which is a real variable, real valued function. Okay, so we assume that f is simply a continuous function. not real analytic. We assume only a continuous function. You can assume around a point, say a comma x naught, okay, around a point a comma x naught, and then we want to ask whether such a equation can be solved. Okay, so let us take the to start with maybe an initial value problem related to this. Okay, so that is the initial value problem looks like x prime t equals to f t comma xt. So I'm not going to write xt all the time. Whenever I use x, it is a function of t. So with x at let me see what I wrote, x at t naught, okay, equals to x naught. X at t naught equals to x naught. So we have that is we are basically looking at, so this is the point t naught, and you are given a point x naught t naught, and we want to look at this is x naught t naught or t naught x naught, whatever you call it as. Let me call it as t naught x naught. So this is t naught x naught. So we are basically trying to look at a curve which is passing through this, a smooth curve which is passing through this, and it satisfies this equation x prime equals to f of t comma xt. Okay, so you can't write the Taylor series. So what is the other way of doing this is look at some equivalent formulations of this. If we are not able to solve some problem directly, we try to look at some equivalent formulations. So integrate this from integrate. So write the integrate from t naught to t. Say t. So when we integrate it, we get x prime t from t naught to t, which is equals to integral t naught to t f of s xs ds, s being a dummy variable. Okay. So this side, the left hand side is going to be, now x prime is there, therefore this is nice. So this is going to be xt minus x at t naught, which is equals to this. So if I write it, the equation, this is x at t naught is going to be x naught, which is given to us, plus this t naught t f of t, so f of s so this is for all t, for all t, wherever, if you are looking at the solution in an interval or in the whole real line, wherever. Xt equals to x naught plus t naught to t into f of s comma x s to s. Right. So what is the way to find a solution for this equation? Right. So this is, both are equivalent. So this is, I can call this as 2. Okay. And this equation as 1. So if x satisfies, this is the first thing. If a function xt satisfies 1, so if and only if xt satisfies 2. So one side we have seen anyway, right? One side we have anyway seen it. On the second side, just take the 2 and differentiate. Use the fundamental theorem, right? So one side we have already seen. This is done above. And the reverse side, differentiate 2. Differentiate 2. So if I differentiate 2, first of all, if we assume that this f is a continuous function, this is what I said in the beginning itself. This f is a continuous function. Okay. So since f is a continuous function, and if you expect x to be a continuous function which satisfies the equation 2, then this f is a continuous function, therefore integral of continuous function is differentiable. Therefore, this xt becomes differentiable. So any continuous function satisfying 2 is automatically a differentiable function. Therefore, if I differentiate this 2 with respect to t, then we get easily by fundamental theorem of integral calculus, by fundamental theorem of integral calculus. You get the we get 1. Okay. Therefore, solving the equation 2 is equivalent to solving the equation 1. So how do we solve the equation 2? So the equation
by
2,
Leibniz.
What? Right. So the idea is to use some kind of iterations, which are these iterations are later came to be known as the Picard iterations. So define the functions like this. So write x naught of t, which is x naught, which is just simply a constant that is given initial value form. And then I define x1t as x naught plus t naught to t f of s x naught s ts. That is, we found what is x naught and put it in this integral to get x1, and keep doing this. That is x k plus 1 is equals to x naught plus t naught to t f of s xkt xks ts. So this we do it for k equals to 1, 2, like this. Okay. So this these iterations are now well defined. That is, because x naught is a constant, if I put the constant here, just put this constant here, I get f, which is a continuous function. Therefore, integral of the continuous function is differentiable. Therefore, x1 is differentiable. And once if you have x1, then just put the x1 here, right? So and keep doing it. So you generate a sequence of functions. Xk is sequence of continuous functions. In fact, they are differentiable functions. Sequence of continuous functions. So the idea is, if this xn converges to say x, okay, so if xk converges to x, okay. So I don't know what is the meaning of convergence and how kind of convergence I will use. Just let us roughly think that convergence means that I can take the limit. Okay, so if you take the limit here, and x naught is a constant and there is a limit here, so I get the limit of xk plus 1, which is going to be x, okay, and this is equals to x naught plus. So this is also, you assume that this limit, if it can be taken inside, this is also going to become, f is a continuous function, therefore the limit goes inside again, and therefore f of s comma x. So that we have the result. Right. So what we need is the only one thing, that whether this limit can be taken inside this integral. All other things are linear effects, right? So all of the things are x and k plus 1 converges to xk. Therefore, limit if I take, that becomes x. And only operations here, there are two operations. One is the integral and the other one is limit. So these are the integral is also a limit process. So basically have the two limits, and whether these two limits are interchangeable or not. Okay. So this we saw in case of even multivariable calculus. The two limits normally need not be interchangeable. The simultaneous limits need not be interchangeable. So that When does such a thing happen? Okay, so that is, we ask a question that suppose you have a sequence of functions, say h and x is a sequence of continuous functions. Sequence of continuous functions, right? Then is the limit of h and x, is this equal to the integral of the limit of h and x? Or we say that if h and x, so is this always true? If they are continuous functions, okay, this is what we used, or we can take over an interval.
Over the continuous function is true.
Yes, continuous functions.
Over the continuous function is true.
For all the continuous functions, it is true. Okay.
Yes.
Any other?
Uniform convergence is required.
Uniform convergence is required. Any other? Okay. So what is the kind of convergence that is required to pass this limit inside? Okay. So let me give you an example here. This is not always true, even for sequence of continuous functions. And if the sequence of continuous functions, even if they converge pointwise. Okay. Say pointwise convergence is not enough. Forget about for any continuous sequence of continuous functions, even if they converge pointwise, this may not be enough. Is not good enough. Why? Let me give an example of sequence of functions. So you can take the functions like this. So start this as -1 and this as 1. The simplest functions that we take is that take 1. Okay. These functions, these are popularly known as the hat functions. That is the right, and we also take something like this, right? So with the height 2 here, and this is -1/2, and like this. So this is the first function, f1, this is f2, and so on. So that is fn's are something like this. So hns are something like this. So h1 and h2. So we define h and x. Which is defining these lines only. So for each n I have to define. So for -1/n to 1/n, if x is not in this, then you take it to 0. That is outside -1 to 1. And the left hand side in this interval, take it as n square x plus n, and 0 to 1/n, take -n square x plus n. So these functions, if you see, h and x, all of them has the property that h and x over the interval -1 to 1 or on the whole real line. So this is going to be that is the area under the curve, is always 1. And the limit of this, okay, h and x, the limit of this goes to 0 if x is non-zero. Okay. If x is non-zero, and the limit function is not well defined at x equals to 0. Okay, not defined at x equals to 0. Of course, there is also another, you can find other sequence of functions where the hx may be defined everywhere. Here in this case, you see that this is not defined here, but you can always find examples where the hx is defined at all points, but still the limit, so the limit function, what I am getting here, is not even a continuous function. Okay, so the limit function here is not even a continuous function. So if it is not even a continuous function, how can it be a function that is differentiable to become a solution of a differential equation, right? So the solutions of this differential equation here, you need the function to be a differentiable function. So you have here the sequence where even the limit function is not even a continuous function. So when does this kind of things happen? That is, this happens when you have the so-called the uniform convergence. Uniform convergence. Okay. So I guess many of you would have seen what is the meaning of uniform convergence. I will just define and write some consequences. And those consequences you can see in the
Sir.
Yeah.
Sir, on previous page, when you define h and x, sir, x belongs to -1yn say 1yn, you say 0, and for -1yn to 0 and n square x plus n. So x is contained both cases, मतलब यहाँ पे दोनों में x है included. That sign x not equals to 0. I'm not getting it.
X not equals to 0. It's a continuous function.
How you define h and x?
At x equals to 0, it is x equals to 0. Take it here. It is n. Here also you take it to 0. It is n.
Okay, sir.
It is a continuous function. I'm just writing the graph which is given here. You write. You take this function. You take the 1 here, and then it is going to be 2 like this, right? So you take. You can always connect the line, right? Line joining these two with 1 and -1. It's only one fixed line which joins these two straight lines. Similarly, the 2 and 2 and minus of, there's only one line that joins it. So I just write that. I just wrote in the general form for any n.
Okay, sir.
These are simply straight lines. They are fixed straight lines. Of course, these functions, there are many ways to define this function. It need not be through straight lines. You can also write the smooth functions. Okay. So the uniform convergence. So I say that a sequence of functions fn defined on I an interval to R, okay, converges uniformly to f
So your screen is paused. So your screen is paused.
Sir, you are not audible.
Hello, can you listen to me now?
Yes,
sir,
sir.
yes.
Yes,
Sir,
My
sir.
screen
repeat
is
from
also
uniform
visible?
convergence, please.
Yes, yes.
Sir, please repeat from uniform convergence.
Yeah, I will repeat that. So can you see my screen now, right? You can see my
Yes.
screen.
Yes, sir.
So the uniform convergence is you have suppose I read this as suppose Fn is a sequence of functions. Okay, we say that converges uniformly. Okay, so we say that Fnx. So we say Fn converges uniformly to F if for any epsilon greater than 0 there exists one n such that Fnx minus Fx is less than epsilon for all n greater than or equals to n, and this such a thing should happen for all x in I. Okay, that is the uniform. The convergence is not just a pointwise, it is also uniform. So that is this epsilon, this n depends only on epsilon. Okay, so this is what we know about the uniform convergence. Okay, so since something is here is happening independent of epsilon, so I could as well take the supremum here. So I could actually take the supremum here. Okay, so this whole thing is going to be still less than epsilon. So this is normally people write Fn minus F, the infinity. So this is known as the infinity norm. We can just use this as a notation. So this is the notation. So this one is notation. You can just use this as a notation. Notation means that instead of writing the supremum mod Fnx minus Fny, Fnx every time, I will simply write Fn minus F in the infinity. Okay. So what happens for the uniform convergence is you have the equivalent criterion, that is Cauchy criterion. So I will not write all the I will write the theorems here, but not the proofs. So Cauchy criterion. What is that Cauchy criterion? Is that for if Fn converges to F, okay, uniformly, if and only if it says for any epsilon greater than 0, there exists one n such that okay, mod Fn x minus Fmy is less than epsilon for all m and n greater than or equals to n, and xy belongs to infinity. Okay, so this is the Cauchy criterion. So advantage of this is that over the uniform over the previous definition is that this definition doesn't require what the f is, okay, what the limit is going to be. Without knowing what the limit is or without guessing what the limit is, we can try to verify this definition. So that's the advantage of the Cauchy convergence variable. So this is one result that we will have. And the other one is yeah. So this the important theorem here is that if Fn converges to F uniformly, okay, uniformly, then F is continuous. Of course, I am also taking Fn to be continuous, sequence of continuous functions. So this is, I can write the proof of this. This is the, this uses a simple, very important argument, which is known as 3 epsilon argument. So you would have seen these things earlier. So one is that you have the 3 points here. So the one point is that from the definition itself, okay, that is Fn converges to F uniformly. Uniform. So this means that you have there exists one n such that for all n greater than or equals to n, you have mod Fnx minus Fx is less than epsilon by 3 for all x in I. So this is first statement. This is one. Second point is that Fn itself is continuous. Fn is continuous for all n. So this implies that at a point x0, okay, for any epsilon greater than 0, there exists one delta, so that whenever you are in the mod x minus x0 less than delta, this implies, say, Fn x minus Fn of x0 is less than epsilon by 3. So this epsilon by 3 argument is here. So once if I want to show that f is a continuous function at a point x0, we estimate this f of x minus f of x0. So this you write fx minus, say, fnx, okay, plus fn x minus fn x0 plus fn x0 minus f at x0. Okay, so adding and subtracting these terms. So if I take this to be less than or equals to, okay, so if I take this to be less than or equals to, then I write the things here. Okay, so now you see f minus fnx is less than epsilon by 3 by 1, and fn minus fnx minus fn of x0 is less than epsilon by 3 by 2, and fn x0 minus f of x0 is again, yeah, at the point x0, just use the 1. Therefore, everything is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3, which is epsilon. So that shows that f is now a continuous function whenever mod x minus x0 is less than delta. Okay, whenever mod x minus x is less than delta. So therefore, if you have a sequence of functions, continuous functions, and if they converge uniformly, then the limit is going to be a continuous function. Okay, then the limit is going to be a continuous function. Another thing what we can show is the integral over f nx dx also converges to the integral over I of x dx, where provided this I is bounded. I is bounded. So how do we do this? Just convergence means that you have to write Fn minus integral over f. So just use the property of the Riemann integrals. So this becomes into Fnx minus fx. Take the absolute value inside. Okay. And we know that this is, I can take from the inside the integral, I can take the supremum always out times the integral I. And we know that if Fn converges to F uniformly, this is less than epsilon times the length of interval. Okay, so if I take this n in such a way that this is going to be less than epsilon by I get this to be epsilon. So therefore, if Fn converges to F uniformly, then we can take this limit. So what is this convergence? Convergence means I am taking the limit what is outside to inside. So equivalently, we write this is what we have. The limit of integral of Fn is the integral of limit of Fn. So if Fn is a sequence of continuous functions, and if Fn converges to F uniformly, then F becomes a continuous function, and you can take the limit inside the integral. Okay, so we have the setup now. That's how we, whatever the question that we asked, we have it now. So that is one this thing that we can try to take the limit inside. That's one. So for that, what we need to show is the iterations that we had, that we define by simple observation, which are known as Picard iterations. These Picard iterations. So we need to show that this xn, this convergence is a uniform convergence. So this xnk converges uniformly to function x. So here we don't know what the function is. We only know the sequence of functions by the definition iteratively defined. So this is the kind of places where we can use the Cauchy criterion. Right. So I need to introduce another class of functions which are known as Lipschitz functions. So the class of functions which are known as Lipschitz. Lipschitz functions. So a function f ex, okay, which is defined in a domain in R2. Okay, where T is a domain contained in R2. Is domain in R2. You can take this domain to be domain means open connected set. I guess some of you know that. So that means it is an open set where I can do the calculus. Basically, open set means that we need we can do the calculus, right? So there are neighborhoods. So connected means that when I take while writing the derivative, if I take x and x plus h, then the x plus h also should contain it. So that's why we require the connectedness for doing the calculus. So that's why we always assume that the domains. So we say that f is Lipschitz. So I can write in the bracket. Once we understand that, we need not write this in the variable x. This is what we require, but generally the definition can be without this variable x. Okay, with obvious modification. If there exists L greater than 0, such that mod f tx minus f, you can take t or s y is less than L into mod x minus y. Okay, for all the points tx and sy belongs to this domain. So since on the right hand side there is no dependence on s, we simply can take this to be t also, okay, because there is no dependence on the right hand side on this s or t on the first variable. So that's why I said in the variable x. So in the variable t also, if you want, you will normally put the one more term here, plus small t minus s. So I will we don't require that. We just require only for s equals to t. We require only for s equals to t. So such functions are called Lipschitz functions. So we want to see what are the functions which are Lipschitz. So some examples, simple examples. So the functions which are constant functions are Lipschitz functions, or the functions which are simply ftx equals to x. Ftx equals to x means if I write ftx minus fty is going to be x minus y. So L equals to 1. So in this case, L equals to 1 will do. L equals to 1 will do. Similarly, you can always have another example. So another example, you can take f tx. So we can take x square plus 1 or x square in x square plus t. Okay.
So please repeat the first example.
First example. Let me write the first example. That is, so what is the first example? F tx equals to x. So in this case, if I write f tx, okay, minus f ty, that is going to be mod x minus y, right? So in this case, L equals to 1. I can simply say L equals to 1. So this is Lipschitz function. So second function, take f tx.
So if L equals to 1, then mod x minus y less than x minus y.
Yeah, it is less than or equals to L. So less than or equals to L.
Okay, sir.
Less than L, you take L equals to 2. Doesn't matter less than or equals to or less. They are all the same. In this definition at least. So L equals to 1, or you can take L equals to 2. If one constant is there, for all the constants above that also it is true, right? So,
Yes, sir.
so in this case, write f tx minus f ty. Okay, it's going to be x square minus y square. So that is why here we take the rectangle. Okay, so the rectangle t comma x, where t lies between 0 and 1, right? So minus 1 less than or equals to t less than or equals to 1, and also x is like a rectangle. Minus 1 to 1 you can take, or minus a to a, or any bounded rectangle, any rectangle. You can take any bounded rectangle. So here it is going to be, now you can write mod x minus y into mod x plus y. So within this rectangle, mod x plus y is going to be less than 2, okay, to mod x minus y. Right? So in this rectangle, because mod x is less than or equals to 1, therefore mod x plus mod y is less than or equals to 2. Therefore, L equals to 2. So the Lipschitz continuity now depends on the domain. Okay, the Lipschitz constant here also depends on this domain. So if the domain is large, then it may happen that the constant becomes small, or it may happen that the constant becomes big. So it just depends on the domain and also the function. The domain and also the function. What are the other examples? The third. Say if I take f tx equals to mod x. Okay. So in this case, if I write mod f tx minus f ty. Okay, so this is going to be mod x minus mod y. And we know that this is less than or equals to mod x minus y. Okay, so you have a formula which says that mod a minus mod b is less than or equals to mod a minus b for all a b real numbers. Okay, so even in this case you have L equals to 1. In this case again, y value equals to 1. Another interesting example is the suppose dou f by dou y, dou f by dou x, okay, is bound, say by m. Not, I don't want to use m. Say by L, L1. Say by A, by a constant A. Then f is substituted. Why is that? So minus f t by. So for this to hold, of course, I'm assuming that the f is partial derivative of f with respect to x is exists. It has to exist at all points in the domain. Then only I can talk about it. So this one is going to be, because I am taking only the t here on both places. Okay, so by the Taylor's theorem or by mean value theorem, it is going to be dou f by dou x. Okay, at a point t, say a point theta x plus 1 minus theta into y, some point which is in the between x and y times x minus 1. So this is our mean value theorem. Okay, so this is the mean value theorem. So therefore this is less than or equals to mod dou f by dou x, okay, times mod x minus y, which is less than or equals to a into mod x minus y. Okay, so this is the partial derivative with respect to x is bounded, then that bound actually becomes my Lipschitz constant. But one of the constant which satisfies this, but actually the Lipschitz constant itself has a definition. Okay. So Lipschitz constant is the one, the smallest L that satisfies the equation. That's the smallest L that satisfies the Lipschitz condition. So such a constant is called, the smallest such constant is called the Lipschitz constant. So this is, I'm saying here, this A is on such L where this is true. Therefore, the function becomes Lipschitz, but A need not be a Lipschitz constant. That's why I was trying to avoid using this L here. L is normally used for Lipschitz constants. Okay, so another interesting example I can tell you is the function which is in the form of a composition. Okay, so the composition of two Lipschitz functions. Say I take f of ty or f of tx is exponential of y square. So I know that exponential of y and y square, both of them are Lipschitz, therefore this should be Lipschitz. So why is that? So we are, so let me take f of say x, okay, and g of y, and then you look at f of g of y. This is what we want. So both are Lipschitz. Then we claim that this is also Lipschitz. Okay. So we claim that is Lipschitz. Why is that? Mod f of g of y minus f of say gx. So this is since f is Lipschitz, I will have this say L1 to mod gy minus gx. Right. Now since g is also Lipschitz, we have, therefore this becomes the required constant so that this circle map becomes Lipschitz. Say for example, I can take, you take for example f of y, okay, f of ty, which is equals to mod sine y. Okay, so this is basically the composition of two maps. That is, one function is mod, the other one is sine y. So this we have seen, this is Lipschitz because of that equality, and this is Lipschitz because the f by dou y is bound. So therefore, mod sine y is a Lipschitz function. Okay, so with this understanding, I will stop it today. So next class I will continue with the proof of this uniform convergence of that sequence.
Thank you.